Hey everybody. Today we're talking about the margin of error of a confidence interval, and in particular, its relationship to sample size. So when the population standard deviation sigma is known, a level C confidence interval for the population mean mu has the form x bar plus or minus z star sigma over the square root of n, where z star is the critical z-score corresponding to the confidence level. Most typically, C equals 95% and the corresponding Z star value is 1.960. And N is the sample size. So the margin of error in this formula depends on three things. The confidence level C via the critical Z star that we saw in that table there, the population standard deviation sigma, and the sample size N. So you can see literally just looking at that formula, there are three ingredients in that recipe. The effects of changing those three values are all predictable. So if you increase the confidence level C, that increases Z star and increases the margin of error. If you increase the population standard deviation sigma, that increases the margin of error. But if you increase the sample size N, that decreases the margin of error. So, for example, suppose we have a confidence level of 95%, a population standard deviation of 6.2, and a sample size of 10. Plugging into the margin of error formula, we get a margin of error of 3.84. I'd like to know what happens when the confidence level is increased, say to 99%, or alternatively, when the population standard deviation is increased, say to 8.0, and then again alternatively, when n is increased to 20. So I want to do each one of these three separately. This is a good place to pause the video, try getting answers to these. First, give me an answer on general principles about when these things are increased, then actually do the computations. So, to start, if we increase the confidence level, we should be increasing the margin of error and getting a wider confidence interval. In particular, if we increase C to 99% but keep the other parameters the same, n equals 10, sigma equals 6.2, the new Z star value is 2.576, we get a margin of error of about 5.05. Again, larger margin of error. On the other hand, going back to C equals 95% and instead changing the population standard deviation to something larger, we expect a wider confidence interval, a larger margin of error. More specifically, if we use sigma equals 0.8, we get a margin of error of 4.96. Again, a wider confidence interval. Finally, if we increase n, we expect a more narrow confidence interval, a smaller margin of error. So plugging in n equals 20 instead of n equals 10, we get a margin of error of 2.72, less than we had originally. In practice, we don't usually control sigma. That's just something that is inherent in the thing we're studying. And the confidence level C is just an inflexible norm that's set within our field of study. We don't generally get to play with that. Usually the value C equals 95% or some other value is just handed to us. So really in that margin of error formula, the only lever that we can pull to affect the margin of error is the sample size. If Z star is fixed via the confidence level C, and sigma is also fixed just on the basis of the thing that we're studying, then the formula that we have can be solved for n to tell us what sample size will be needed for any specified margin of error. And the result is n equals quantity Z star sigma over E whole thing squared. And this is useful when you're planning data collection. You have a certain margin of error that you're targeting, known Z star and sigma. This gives you the sample size that is needed. For example, suppose we have a manufacturer that wants to determine the mean weight of a certain sort of nail that they're making within 0.2 grams. We'd like to find the sample size necessary to do that with 99% confidence if the population standard deviation is 0.5 grams. By the way, I know that grams are a unit of mass, not of weight. I am being kind of loose with my language here. Thanks for understanding. It gets awkward if I don't do that. All we're going to do to solve this problem is to plug into the formula that we saw on the previous slide. N equals Z star sigma over E, quantity squared. And when we do that, we get N equals 41.5. Now, we need to round this because it's not actually possible to weigh a half a nail, at least in the way that it would be meaningful for this example problem. The rule of thumb is that you should always round sample sizes in problems like this up. And the reason is that a larger sample size is the more conservative way to go. If you decrease the sample size, you potentially increase your margin of error. And since here we have demanded that our margin of error be within 0.5 grams, increasing the margin of error is a bad thing. To be more conservative, we always round the sample size up, so we should weigh 42 nails. Here's one more example for you to try. I recommend pausing the video, working through this problem, then unpausing it and seeing my solution. Suppose we want to estimate a person's weight within 0.4 kilograms using a 95% confidence level and a scale with a standard deviation of 0.8 kilograms. Find the minimum sample size required. So, plugging these values into my formula for the sample size needed for a certain level of confidence, standard deviation, and margin of error, I get 15.4. Now, while formally that should be rounded down to n equals 15, we instead want to round this up to 16. We should do 16 weighings in order to achieve a margin of error no worse than 0.4 kilograms. By rounding up, we ensure that our margin of error goes down a little tiny bit, not up a little tiny bit, potentially violating that 0.4 kilogram margin of error restriction that we have.